Okay. Hi, everyone. Welcome to our 10th session of the MedAI group exchange sessions. This week, we are very happy to have Edward Choi from KAIST here with us to talk about his research on learning the structure of electronic health records using graph convolutional transformers. Edward is actually an assistant professor at KAIST, the Korean Advanced Institute of Science and Technology, and focuses on machine learning, healthcare analytics, and natural language processing. He did his PhD in Georgia Tech, advised by Professor Jimeng Sun, and focused on interpretable deep learning methods for longitudinal EHRs. And he was also at Google Health Research, developing deep learning models for predictive healthcare. So thanks so much, Edward, for joining us today. And before we start, do you have any preferences on how you'd like us to ask your questions? Like, do you want it to be, can we interrupt you in the middle, or would you like it at the end?
No, please interrupt me anytime you want.
Awesome. Okay. Yeah. So as always, let's try to make this session as interactive as possible. And without further ado, let me hand it over to Edward.
All right. Hi, thanks for the invitation again. I mean, giving me the opportunity to talk about my research and the kind introduction. So let's get started. So the title of the talk today is, as introduced, learning the graphical structure of EHR with graphical convolutional transformer, or GCT. So this is the table of contents. So we will very briefly talk about what EHR is, since I'm assuming that everybody's already kind of familiar with what EHR is. And then we'll take a journey through a simple EHR modeling to using the structure of EHR, then actually learning the structure of EHR. So, which will be the focus of the talk. And if time allows, hopefully I can introduce some of the most recent works that I'm doing with my students, which is multimodal learning with transformer-based architecture. And then we can, if there are questions, I'll answer them. All right. So this is the picture that I usually use to describe what EHR is. So EHR is a comprehensive data set that contains everything that happened to a patient at the hospital, and which is usually stored in a relational database. So it consists of a lot of tables, but to the user, on the user side, which is usually the doctor, this is the user interface. So when a patient comes to the hospital, and sits with the doctor, then the doctor pulls up a screen, then the doctor will see a lot of various information, such as the name, age, and the problems, past history, medication history, maybe allergies, such and such, which are all coming from different tables of the relational database. So I'd like to say that EHR is a heterogeneous multimodal data, which consists of demographics, medical history, encounter records, medication and allergies, lab tests, radiology images, such and such and such. But these are semantically different. I'm sorry. Oh, I thought there was a question. No. Okay, I'll just continue on. So these are semantically different information, but computationally, we can think about maybe 4 or 5 different modalities. So which mainly EHR, when we talk about EHR, we mainly talk about structured codes, which are diagnosis codes or medication codes or procedure codes. So this is that kind the figure for those kind of like structured codes happening over a sequence of time or a sequence of visits or encounters or admissions. And there are, of course, obviously free text notes, such as clinical notes, physician's notes, or discharge summary, such as such. There are continuous information, such as blood pressure, or all the vital signs basically are continuous values. Radiology images, or not just radiology images, but any pixel value data is also another form of modality. Time series data, or multivariate time series data, such as EKG or EEG, they can be seen as time series, or they can be converted to a spectrogram using Fourier transform. So I would say there are about typically 4 or 5 different modalities in a single data set, which is observed from, which is all partial observation of the true state of the patient at a given time. So if we want to really understand what the patient state is, or the latent state of the patient is, we should be looking at as many modalities as possible, right? So keeping that in mind. Oh, also, I'd like to emphasize that those modalities or those different sources of information, they don't just float around independently. They're all connected to each other because, as I said, EHR are typically stored in a relational database in multiple tables, and each table has foreign keys and primary keys. So if you start connecting them, all the foreign keys into different tables, then you can view EHR as a graph or hierarchical graph, more specifically like this. So there's usually patient ID at the top, and then patient makes multiple visits over time. And then at each visit, you start with a set of diagnosis codes and some family history or some auxiliary information. And then given a diagnosis or maybe a physician suspecting a diagnosis, they can order a procedure such as taking an X-ray or doing some tests, or they can order medication if the symptom or if diagnosis is pretty certain. So I would say the diagnosis leads to treatments like medications or procedures. And then some procedures, they usually lead to more information such as continuous values that are observed during a lab test or something like that. All right, so I would say it's a very comprehensive, multimodal, heterogeneous graphical data set. Right, given this, we'll start with, just in case there are participants who are not familiar with EHR or who are not familiar with making prediction models out of EHR, we'll just take a look at the very, very basic stuff. So this is coming from a pretty old project, which starts from 2015, which is the first time that I tried to come up with a deep learning model for making predictions using longitudinal outpatient records. Which was the work that I had been doing, that I was doing with as an intern at Sutter Health back in 2015. So a pretty long time ago. So back then, I was asked to predict heart failure diagnosis in the future, given a sequence of outpatient records. So it was outpatient records that I was looking at, and I viewed a single patient as a set of a sequence of visits. So a single patient could be seen as a sequence of visits, and each visit contained multiple codes and different number of codes at that, actually. So in the first visit, the patient could be diagnosed with cough and fever, and then prescribed with Tylenol, and then maybe get IV fluid just for just to make them feel better. And then at the second visit, maybe it was a light visit, so just cough and chill. And then the third visit is a bit heavier, so the patient was diagnosed with fever, prescribed Tylenol, and then this time actually taking an X-ray was needed. So it's mathematically speaking, this is a patient can be seen as a sequence of set of variable number of codes. So it's a set of codes that occur over time. And obviously, this is it's not a regularly occurring visit, because a patient could be making outpatient visits maybe today, and then maybe a month from now, and then maybe 2 years from now after this. So it's an irregular time series data. But for the sake of argument, we'll just keep them. We'll just ignore the regularity or irregularity at the moment. So given this, usually what people have been doing before deep learning was one of the simplest thing that people could have been doing was to just aggregate the entire patient record over time. Maybe we have an observation window. We'll just decide that, okay, we're gonna just take a look at past 1 year history, or maybe past 2 years history, and then aggregate the information that occurred all throughout the entire observation window. So simply we can count them, just how many times cough occurred twice, and how many times fever occurred twice, how many times chill occurred once, and chest X-ray once. So it's so we can represent a single patient as a very long, sparse vector. So the dimensionality of the vector would be the same as the entire number of events that could happen to the patient. And then each dimension would indicate the number of times it actually occurred. So it's a count vector, basically. So obviously we can do it, but we can do better than this. If we're predicting heart failure, for example, then maybe a cardiovascular expert could sit with an IT engineer and then tell the important features to focus on to actually make a prediction. But here we're just gonna use the counting vector example. So usually when I was using this data, Sutter Health data, there were about 10,000 diagnosis codes, 20,000 medication, and then again 10,000 procedure codes. So all in all, about 40,000 kind of events that could happen to a patient. So that's why I wrote 40,000 dimensional vector here. So given this, this is now the patient representation vector, which is a very naive one. We can put it through a logistic regression or support vector, whichever favorite classifier that you want, and then make a prediction. And it's a binary classification. So if it's 1, then yes, this patient will have heart failure in the future. If it's 0, probably not. But instead of actually using a simple counting vector, the first thing that I thought of was to use RNN, because back then it was actually the kind of the early era of deep learning NLP. So RNN was like the go-to model, and obviously because a patient could be seen as a single as a sequence of visits. So maybe I could put each visit to the RNN, but then I would have to come up with a way to actually represent each visit first, so that I can get a visit representation, and then I'll have 3 visit representations. I'll just put them into RNN sequentially. So in order to get a visit representation first, simply what we can do is we can represent each visit as a binary vector. So at visit number 1, cough, fever, typhoid, 4 things happen. So it's the same dimensionality. So it's a 40,000 dimensional vector, but only 4 dimensions would be 1. All the others would be 0 because only 4 things happen. So it's an extremely sparse vector, so very inefficient, but we'll just go with this first. So this will be our x1, which is a sparse binary vector. And 4 things are tick to 1, all the other are 0. And then we can, because this is a very high dimensional vector, we can maybe squeeze it into a 128 dimensional vector or 256 dimensional vector. Just it's a hyperparameter, just like how people use different, maybe when people try to use word embeddings like word2vec, or these days BERT uses a bit larger dimension, but back in the day, word2vec or those kind of word embeddings use 128 dimensional vector or 256. We can do the same thing. We can actually try to represent a single visit with a 256 dimensional vector instead of 40,000 dimensional vector. So we just simply compress it into a lower dimensional space. And then once we have the visit representation, which is V1, we can start putting that into the RNN. So we put visit number 1, the visit number 2 sequentially into the RNN, and then all the way until the very last observation, until the very last encounter. Then we'll have this HT, which is the memory cell of the RNN, as the patient representation vector now. So instead of using a count vector, which is a bit naive, we can use the last hidden layer of the RNN as the patient representation vector. And then after that it's all the same. Once we have a patient representation vector, we can put it into a logistic regression, SVM, whichever you want. But usually people use a logistic layer after the hidden representation. So we'll do the same as well. So then the output is between 0 and 1. Again, 1 being yes, this patient will have heart failure, 0, no. So it's a very straightforward architecture. From now in 2021 perspective, this is extremely simple approach. But back in the day, this was kind of the state of the art, and nobody actually knew that if it would work or not. Okay, so I just tried it out. So given this on the patient records that I was provided from Sutter Health. So it consisted of about 30,000 patients, and about 4,000 of them were heart failure cases, so who were actually sick, and the rest, 29,000, were controls. And I was given about 1.5 years history, so about 18 months. So during 18 months, each patient on average made about 20 outpatient visits. And since I'm not a cardiovascular expert, I just use all the features that I could use. So entire diagnosis codes, medication codes, procedure codes. So entire 40,000 medical events. And obviously case control matching criteria was not designed by myself. It was designed by the Sutter Health healthcare experts. So given the status, given this feature, I just tried out the previous RNN based approach, and compared to the classical approaches, which is logistic regression, SVM, NLP, CAN, and this kind of stuff. GRU, which is a variant of RNN, as I'm sure everybody knows. So these GRU, 2 variants, GRU, outperformed the classical approaches, which is very obvious from today's perspective, since these are not sequence models. So in order to use these models, you have to somehow aggregate the information. So I just use counting vectors here, but instead of using counting vectors, if you use the sequence of events, then it is a bit more easier for the model to see if a patient is getting better or getting worse in terms of in terms of his or her heart condition. So it's making a way more accurate prediction. And by the way, so these two variants are actually the difference between using the temporal information and not using temporal information. So temporal information being, the irregularity of the visits. So the ones that you do use, the one that does use the temporal information is I just appended the time difference or time duration between consecutive visits as an additional information to the visit embedding. So once I have the visit embedding, I just append maybe one or two temporal time representations, such as the log of time duration or the inverse of time duration or normalized time duration, such the kind of stuff. So if you start using those that temporal information, you get a very marginal improvement. So which is I guess this is also natural, given that the RNNs are not actually designed to handle irregularities. So if you're interested in that kind of aspect, you could try to look at neural ODs or recent neural processes. All right, so this is the very, very basic stuff. So you just represent each visit as a one multi-hot binary sparse vector, and then you roll them up to lower dimensional space, and then you put them into RNN, and then you can do a back prop and then update the parameters until your satisfaction. So even though it's a very simple approach, it does work pretty well until even today. This is a very strong baseline. It's actually kind of hard to actually beat this very simple baseline unless you are in a really specific situation where you have very small amount of data, or when you're dealing with very rare disease. Except for those kind of like special cases, this RNN-based approach actually works pretty well. All right, so given this very simple baseline, we'll move on to the second subtopic of today, which is actually using the structure of the EHR. This is the work that actually, this is the last project that I did as a PhD student back in 2018 with collaboration between IBM and also Sutter Health. So as I said, EHR, the entire data set, can be seen as a hierarchical graph, and especially also when looking at a single patient. Now we're looking at one patient by one patient because we're making predictions for each patient. So given a single patient, they can be seen as also a hierarchical graph. So at the very top sits the patient ID, which is the node, and then right beneath there are sequence of nodes over time, where each node represents an encounter. And then underneath is diagnosis code nodes, and then underneath is medication orders and procedure orders and that kind of stuff. So if you simplify this, so if you just throw out all the demographic information or the smoking history, family history, social history, if you just throw them out and then only just retain the diagnosis information, medication, and lab results and procedures, then you can represent the former graph like this. So it's a simplified version. So a single patient can be seen as again a sequence of visits, and a single visit is now a hierarchical graph. So at the top sits the diagnosis layer, and then beneath sits the treatment layer, and then underneath sits the result layer, if there are lab results. So given this hierarchical graphical structure, what we did so far, or what I did before mine, is to actually represent a single visit as a binary sparse vector, multi-hot vector, if you will. And when you represent a single visit as a multi-hot vector and then compress it into lower dimensional space, what you're essentially doing is converting each code to its corresponding vector representation and then summing them up. And then that summing up is the way to represent a single visit, because at each visit, multiple things that happen at the same time. So I thought maybe just simply summing them up was a sufficient way to represent a single visit. But this is actually flattening this hierarchical structure. If there is a hierarchical structure, why not use it? Why should we just compress it, and why should we just flatten everything and then just lose this valuable information? Because this information, actually, this red edges contain the physician's thought process or decision process. So it actually, they do contain clinical information or clinical domain expertise. But here, if we do this, we're just throwing them all out. So it's probably a bad idea. And if you do this, all burden falls on the RNN or the upper layer where visit information are aggregated. All burden falls on that part to figure out the relationship between multiple codes. So probably not a good idea. So what I did in MIME was to actually propose we should take a look at the structure of EHR and then exploit it if possible. So simplifying, again, that former graph is we have a sequence of visits, and then each visit consists of layer 1, which is diagnosis layer, and layer 2, which is the treatment layer. And unfortunately, when I was working on MIME, I wasn't able to incorporate the lab results. So there are only 2 layers. And so I came up with a new concept called diagnosis object. So each diagnosis, in this case, there are 5 diagnosis objects. So diagnosis object 1 consists of just fatigue. Diagnosis object 2 consists of cough, and its related treatment codes or treatment group. And the second, obviously, like DX object 3 looks like this, 4 looks like this, 5 looks like this. So now we are seeing each visit not as a sum of codes, but sum of diagnosis objects. And then each diagnosis object consists of 1 diagnosis and its related treatment codes. So it's a bit more hierarchical. So that's why the name of the paper is multi-level embedding. So what the essence is we want to use multi-level information when deriving the representation of the visit so that we can use the physician's domain knowledge. And this is the actual the formula of the formula of the model, but which is not very important because this is all just detail. The important thing is trying to capture the hierarchical information, which can be done in many different ways. Here, what I did is, so what we want is the final patient representation, which is H, and H consists of multiple V's, which is visit representation. And the essence of the MIME is to actually come up with a new way to represent the visit representation V, which is so H is the entire sequence of visits. V is a single V visit, and then single visit V consists of multiple diagnosis objects. So there are this red box here. So it's a bit hierarchical. And then we try to derive the representation of the diagnosis object. We use something called bilinear relationship between the diagnosis and its related and its relevant treatments. But you can think of this as a very specialized graph neural networks or graph convolutional networks, because we are dealing with graphs now, which are unidirectional. First of all, it's unidirectional because the arrows go like this. So it's a unidirectional hierarchical graph. And if you have the adjacency matrix, then you can simply use graph convolutional neural network instead. So MIME is just a very specialized graph neural network.
Hey, Edward, can I ask you one quick thing?
Sure.
So can you go to the previous slide once?
This one?
Yeah. So my question is that how do you actually understand which treatment is applied for which diagnosis? So do you collect that?
Oh yeah, so that's a very good question. In this, when I was working in this project, so these red edges were already there in the data set, which was very fortunate for me. So the data set consists of medication order table and the procedure order table and lab order table. They had a column named reason, which is where you write which diagnosis code led to making this order.
Okay, because ideally, if you look at Cerner, Epic, any common database, in those databases, actually, they don't save really for the reason in terms of structured code. The reason is actually mentioned in terms of free text.
Right.
So that was my main question, that how do you correlate that information? Did you parse that information using another set of NLP to like connect it, or how you did that?
Fortunately for this case, the reason was not stored in free text, but it was actually stored in the diagnosis ID. So there was just ground truth information given to me. So,
but ideally, that I don't know if you studied that. Like ideally, this kind of coding has 70% accuracy.
Right, right.
And
So there's a
yeah.
lot of noise going on. Yeah.
Yeah.
Sure.
Do you even like investigate that noisy part in your model? Because I would imagine that there are a lot of noise also for the coding the reason.
Not in this part, not in this project actually. So
Okay.
the next project, which is the GC graph convolution transformer, that paper is the reason, the motivation was exactly what you said here. The first of all, not all data set contain this kind of reason information, and second of all, if there are, it's still noisy. So we would like to do better than this. But in this MIME paper, I wasn't paying attention to those kind of details. It was the first time actually I realized that there was a graphical structure inside EHR. So I was just focusing on trying to exploit that.
Okay. And can you go to the next slide? Sorry, I was asking multiple things probably. Can you go to the next one once? Yeah, here. So here actually when you consider as a treatment, you are mainly considering medication and procedure both as the treatment information, right?
Right.
So for example, like cardiac ECG is a procedure, while your fluids are mainly, or these other medications, they are just medications, right?
Sure, right.
Okay, so you consider both of them as part of treatment.
Right, because I wasn't actually using the specific information that comes with medication or specific information that comes with procedure, such as like medications come with drug routes, drug dosages,
start date, end date, yep.
Right. I wasn't using them in this project, so I just didn't really. There was no need to separate between like medications and procedures and labs. I was treating them all as just codes, structured codes.
Okay. Because since it's a temporal model, so that's my main curiosity, right? Since it's a temporal model, the time point doesn't really start with the same time point as the diagnosis.
You mean for the different number of visits?
Yeah, for the different, for example, if I consider teeth visit, and I don't know, maybe you get a medication, benzotens, and for the cough, the start date may not be the teeth visit immediately. So may start date maybe like T+1 visit,
Oh,
like
I see. Yeah,
because
right.
Those are the temporal information that is actually included inside the treatment database. You can say like treatment database, right? Also, the cardiac EKG may not be performed exactly at the T8 visit. It's ordered at the T8 visit, but may be performed sometimes else, afterwards.
Yeah, I mean, you're absolutely right. So I wasn't. So all medical events during a single visit, such as medication orders, diagnosis, or procedure lab, they all come with their timestamp, and I wasn't using those timestamp specifically. I was just treating all. I was assuming they were all happening at the same time, or at least they were related to the single visit, because they all did happen at the single visit. Of course, the actual time of event, time which the individual separate events took time is all different, as you said. But I might be going ahead of my the contents. But when I start using those information, like individual timestamps or dosages or routes, I didn't find them to be too dramatically helpful, which is depending on the task. Because if you're simply just trying to predict the long-term chronic disease such as heart failure, then I'm not sure if using the timestamp of medication orders or using the timestamp of the lab measures, those kind of stuff is really important, because we're talking about
but imagine that you have ordered some kind of like cardiac medications, and the order has been placed, but the patient never got that particular medication, so it would have a huge impact on their final outcome, right? So like this kind of thing, like the order placing doesn't really mean that the patient, that procedure or that medication was actually taken by the patient.
Sure. Yeah, that is also correct. So in that case, we wouldn't, simply looking at the EHR wouldn't be enough. We would have to actually see whether they actually went to the drugstore like CVS or Walgreens and then actually made the order or took the medication from those stores. So I heard that there was a data set called Truven something, which is actually So you can.
So that is actually the claims data set. That means the patient made the claims for those medications.
Yeah. But then again, we can also suspect we can still assume, or we can still like imagine the patient taking the medication, but not actually taking them.
So that's why actually, so the another route that people usually take is to also parse the physician follow-up note afterwards, just to see that if the physician mentioned in the note that the patient is taking this medication, during the investigation.
Yeah, that's also one of the topics that I'm very interested in, which is to use all the nodes in the EHR as much as possible. But there are just so many nodes. It's if you try to put them all into a single model, that your model will blow. Your memory will blow up. So trying to think of a way to do it efficiently these days. All right.
Thank you.
Thank you for the question. All right. So since this was the first model that I came up with to trying to use the structure of the EHR, I tried to compare this with a lot of baseline, which is basically just different ways to embed visits without using structure. So just linear embedding, which is simply just adding the vector representation of all the codes that happen at the same visit, simply adding them, or maybe putting them through a nonlinear activation function, or maybe adding more extra layers to make it even more powerful, or other previous works of mine that try to use structure of the EHR in a different way, or trying to use domain knowledge, like and external medical ontology. But basically, these are all just different flavors of coming up with visit representation without considering the structure. It's just so that we can try to see if MIME is actually doing something better than these different varieties. And the dataset was exactly the same thing. It was the Sutter Health dataset. So what I thought is, as I said, you can trying to learn or exploit the physician's decision process is you can see it as a way of regularization, because you are actually trying to limit the way the different codes are interacting with each other the codes that I'm talking about is the codes that occur during the same visit. So we're actually using the graphical information. So some certain codes can only interact with another code, and so we're limiting the expressivity of the model, but we're hoping that it'll help, because we're limiting in a way that is inspired by this physician's thought process. So if you can see this as a regularization, then you can expect that it'll work better in the lower data scenario. So what I did here is just use a different number of training samples, but keep the number of test samples the same, but we're using different number of training samples to see if it actually performs better in lower data regime. So and it does actually. So the top two here are different. One is MIME and another is MIME auxiliary. So it's just MIME using an auxiliary multitask loss function. And then especially when you use a smaller number of training samples, it actually outperforms all the others by some margin compared to when you're using all the entire training samples. So this is experiment number 1. And in the same experiment, what we tried to look at is, if the visit is not very complex, then there's no need to consider the graphical structure. If a single visit consists of only one diagnosis and one medication, then there's nothing to be confused about. If only in the case where there are multiple diagnosis codes and multiple treatment codes happening at the same time, that is where MIME should shine. Because in the other, so if the visit is not complex enough, why not just simply adding them up? There's no difference between MIME and the either baselines. So you can see that. So D1, D2, D3 are three different groups with different visit complexity. So when I say visit complexity, it just means how many diagnosis codes and many treatment codes there are in a single visit. So D1 is the least complex and D3 is the most complex. And in the least complex, the difference between MIME and all the other baselines are not very significant. But if you go to D3, you can see that the performance difference between the other baselines, the different flavors of flattening the visit structure. So those versus the MIME variants are the performance gap is pretty large. So you can see that when the visit structure becomes more complex, then using physician's decision process is helping. And the third one is, since we established that this kind of works as a regularization method, we thought maybe we can try a different task. So the first task was predicting the heart failure in the future. This task, the second task, is to just simply predict the next visits. So a single patient can be seen as a sequence of visits, and a sequence in each visit. There are multiple diagnosis codes happening. So what we are doing here is given the visits so far, trying to predict the next visit where the number, all the diagnosis codes that will happen in the next visit. So it's just like a sequential diagnosis code prediction, just like language modeling, but in a bit more Medicare in a clinical setting. So we divided the entire diagnosis codes into 4 categories, which are really rare ones to all very frequent ones. So, for example, like hypertension it would be included in this bucket. Very rare disease like genetic disease or like hereditary disease would be included in this bucket. And we thought maybe rare disease equals low number of training sample. So mine would be helpful in either this bucket or in this bucket. Interestingly, not so much in this bucket because it's so rare. Only there is about 0.01% prevalence rate in the training samples. Like, so the diagnosis code that included in this bucket happens, like 1 out of 10,000 samples. So yeah, so which is really, really rare. But so I guess nothing really works here. Except MedToVec. We're not really sure why MedToVec actually outperforms all the other here. But starting from the second bucket and so forth, you can see the difference between MIME and all the others are actually, so here, GRAM and MIME, they perform pretty close. The performance is pretty much similar. But here in the rarer disease group, MIME actually outperforms all the others by a significant margin. So we can reconfirm that this is working as a regularization method. So the conclusion is that the EHR structure reflects physician's decision process, and it is a good idea to use them if it is possible. And as was it Iman? As Iman suggested, not all data sets contain the reason information. So that is why we come up with the GCT now. So this is the last project that I did before leaving Google and joining KAIST. So these were the co-authors, and the motivation was that the red edges, which are the reason information. So the red edges are not always available. So for example, open source data sets such as Mimic or EICU, they don't contain red edges, and claims data, obviously they wouldn't contain those edges. So only I've seen many examples of EHR data set when I was working at Google, and I think only one data set contained these red edges. So it's a pretty good idea trying to generalize the previous MIME approach too, so that you can use it in most of the cases. So, and again, another second motivation was that the association edges are probably very noisy, because this was also observed by my fellow colleagues at Google, physician colleagues at Google. They said that if your EHR system requires you to put a reason when you're ordering something, you will just write down anything because it's just time consuming. You don't want to write down specific reasons every single time you order Tylenol. So you just put whatever you want to, and it's going to be pretty noisy. So these were the 2 motivations. And so we can think of 2 scenarios where if the structure information is available, if you have a data set, and if your data set luckily does contain the structure information, accurate structure information, then you can use very specialized model for exploiting that structure, which is, for example, you can just use MIME, or you can just use any different flavor of GCN or GNN these days, graph neural networks, graph attention networks, graph pooling networks, whatever you want to. But if, unfortunately, your data set does not contain that red edges, or if it's really noisy, then what are you going to do? Are you going to go back to using just bag of codes approach, or can you do better? And so the co-authors and I thought we could do better than that. So what idea was actually inspired from Emily Choi, which is one of the co-authors. So she said, what if we just start with a fully connected graph and then sparsify? So when I say fully connected graph, let's look at a specific example here. So we're always talking about just a single visit, because if you have a sequence of visits, you can simply put them into a sequence model. But when the focus is how to represent a single visit, and there's a visit node here, and let's assume that this visit contained 5 codes, and we don't know exactly how these codes are related to each other. We just know that they're there, and there is probably a hidden relationship between those codes, but we don't know we cannot observe it. So simply we start with implicit fully connected graph, and then as you learn or as your model learns to do something. It depends on what kind of downstream task, what kind of supervised prediction task it does. If it could be mortality prediction, it could be heart failure prediction, it could be anything. But while it is learning to do that target task, maybe along the way it can learn to sparsify the graph and then try focus on a bit more useful connections between certain subgroups of codes. So this is the basic idea. And when we thought about this idea, I spent some time working on just imagining how we would do this, starting with a fully connected graph and then sparsify. I was trying to think of a way how to do this more as cleverly as possible. And then I thought about self-attention mechanism from transformer. So if you are familiar with self-attention, you can immediately, this is probably not necessary, but just to give you a brief introduction to self-attention. So attention mechanism is you want the model to decide what information is important for making a decision. So it's not you giving the attention, it's the model learning to attend to different pieces of information. And self-attention is if you have a sentence like this, like I like going to movies, termination symbol. So there are 6 tokens or 6 nodes, if you will, because a sequence could be seen as a chain form graph. So it's 6 tokens or six nodes. And self-attention is each node giving attention to all the other nodes, and you're iterating this process for every single node. So I can attend to like going to movies and the termination symbol. In the same manner, like also can attend to I going to movies and termination symbol, and then going can also attend to all the. So it's the number of connections or number of attentions would be the square, the 36, which is which is 6 squared, 6 being the number of tokens. So if you put it into the scale dot product of transformer, which is a QKV operation, it looks like this. So QKV operation of transformer is softmax of query vector, a query matrix, key matrix transpose divided by the just normalization factor, and then multiplied to the vector matrix. So this part, the softmax part, this part leads to this kind of attention map. And this V matrix is just simply the node representation. So I like going to movies, termination symbol. They are the word vectors or word representation vectors. So this part is actually the interesting part. So the first row is the attention strength given by I, the first node, to all the other nodes. So there's obviously a self loop, so self-attention. So I is giving attention to itself 50%, and then 10% of the attention is given from I to like, and then 20% of the attention is given from I to and movies. And the second row is the attention from like, is the second token. So like is giving attention to I, 20% of it, and 60% of the attention is given from like to itself. So there's another self loop, and then and so on and so on and so forth. So there are 6 rows because there should be 6 sets of attentions. If you simply multiply this attention map with the vector map to the value matrix here, or the word embeddings, then you would obtain this outcome, which is just simply weighted sum of the attention and the word embeddings. So this is the first row. So first row being, this is a weighted sum where the weights are coming from the I's attention. This is a weighted sum where the weights are coming from the likes attention, so on and so forth. So keeping this in mind, if you're familiar with graph neural networks or graph convolutional neural network, the process is pretty much similar. So if you have a graph that looks like this, so there are 6 nodes and 1, 2, 3, 4, 5, 6, and the connection looks like this, then you can represent this connection with this adjacency matrix, which is a bit normalized because a single node can be connected to multiple things. So we want to normalize the strength of the edge weights. So here, node number 1 is connected to itself. So there are always self-connections. We're assuming there is always self-connection. So first, node number 1 is connected to itself, and 2 and 3. So there's values here. And then second node number 2 is connected to 1, itself, 4 and 5. So 1, 2, 4, 5 have the non-zero values, so on and so forth. And a single layer of graph convolution is just simply multiplying this adjacency matrix with the node embeddings, and then obtaining the outcome, and then putting it through a nonlinear function. So at least this much, before the nonlinear activation part, at least this much is just simply a weighted sum of the node embeddings where the weights are coming from the adjacency matrix. So you can see the similarity between the two. So here, in the self-attention process, in the QKV operation, the attention maps, they represent the connections between the nodes, and the connections are determined by the model. It's a purely data-driven process. In the graph neural network, the connections are coming from the data set itself. So it's a purely a priori knowledge-driven process. So that's the only difference between this and this. So, and even mathematically, they're pretty much similar. So graph neural networks can be written as this. So this is D inverse A is the normalized adjacency matrix. CW is the node embeddings, and NLP is the nonlinear activation function. This is a single layer of graph convolution. Single layer of transformer encoder block looks like this. So there's QKV operation, and followed by a set of NLP functions. So here, this part, the adjacency matrix part and the self-attention part, they're serving the same role. It's just representing the connection between the nodes or the relationships between the nodes. And then this part, CW or V, or this part, is a node embedding or the token embedding part. So there's like a one-to-one.
So Edward, so also for this one, you are assuming the graph is unidirectional, right?
It could be unidirectional, it could be bidirectional. In this setting, it really doesn't matter because
I just wanted to understand the adjacency matrix creation, because previously when you are describing the attention, so the adjacency matrix you also calculated by adding the parent node, right? So I just wanted to understand, for this adjacency matrix, are you also adding the parent nodes as adjacency or not?
Here, so in this example, this is the matrix is symmetric, so it's bidirectional. So if one is connected to, then two is also connected to one. But there can be different varieties. You can keep this into unidirectional form, or you can have like asymmetric connections between different nodes. So that's probably up to your choice. And as for transformers attention, there is no restriction whatsoever. The attention map is solely determined by the models. If the model was, right. Okay.
But for your case, actually, you have the semantics between, like semantic difference between the two layers, right? One layer is your treatment and one layer is your diagnosis, right? So I just wanted to understand that if you follow the same transformer convention also for this kind of semantic difference level graph.
In this work, I don't. I just use this transformer. Okay. So I don't. Actually, no. There is. You'll see in a couple of slides actually. Okay. So there's all right, but very relevant question. Thanks. All right, so there's one-to-one responders, and so given this connection between the graph convolutional transformer, graph convolution and the self-attention, I was assuming that maybe if this is real underlying true graphical structure of the visit, then maybe we can somehow use self-attention to learn this as we go. So hopefully we can guide transformer to learn meaningful graph structure while learning for the supervised prediction task. So what I did is, so how do I guide the transformer to learn the ground truth graphical structure? Is you need to start somewhere. So what I thought was, maybe we can use the probability, just the simple statistics that occur in the EHR dataset. So what I focused on is the conditional probability. So here, this is a single visit, and we don't know the true structure between the different layers, the diagnosis layer, treatments layer, and the lab result layer. We don't know the ground truth structure, but what we do know, what we can calculate, is the conditional probability between pairs of codes. So for example, what is the probability that you see EKG given chest pain in the same visit? And in the same manner, what is the probability that you see QRS duration in the same visit when you see a given benzonatate is also in the visit, something like this. So based on this conditional probability, you can fill in this conditional probability matrix where the rows and columns represent the codes. So here, we always have the visit node, and then followed by diagnosis nodes, Medicaid, and the treatment nodes, and the lab nodes. And you know that the visit node is connected to all the diagnosis codes. So these are all just given, and there should always be a self loop in order to make the learning process feasible. And then some cells or some connections are forbidden. For example, this is a restriction that I'm just putting in. So for example, you don't want fatigue to be connected to fever because you want this hierarchical graphical structure to be learned. So there are certain restrictions that you can just put it as you see fit. So these conditional probabilities are filling in these white cells here. So which is different. So for example, what the conditional probability can be between chest pain and EKG. And when I say, and if you use the same conditional probability for here, for here and which is here, then it would be a symmetric matrix. But the conditional probability can be actually, it is not commutative. So the probability of EKG given chest pain and the probability of chest pain given EKG can be different actually. So you can use asymmetric matrix here instead. So that's actually what I did. I ended up using asymmetrics conditional probability matrix P. So this is our data. This is our domain knowledge driven prior. So this is kind of like a pseudo true ground structure, but this is not actual ground structure. This is like a pseudo ground truth structure. So this will be our prior P. And then using this, what we do is, okay. So using this, what do we? So I guess that I don't have the slides for this. So using this, what we did is, so we start with the graph convolutional neural network where the adjacency matrix is exactly P, and then starting from, so we have a single layer of graph convolutional neural network, and then after that we stack transformers instead. We don't simply just repeat this adjacency matrix over and over again. What we did is we just embed nodes using this adjacency matrix once using graph convolutional neural network, and then following that is set of transformer blocks where the transformer blocks. So now we regularize the transformer attention maps to be not to diverge too much from the previous attention matrix. So here, this is what we're doing here. So we do attention regularization with KL divergence term, where we want in the first layer, we want our self-attention map not to diverge too much from the conditional probability P. And then in the consecutive transform blocks, we don't want our current attention map to diverge too much from the previous attention map. So we are gradually learning or gradually modifying this pseudo true structure into attention map, which is more suitable to making a prediction, for example, like heart rate prediction or mortality prediction, whatever prediction you want to do given your supervised task. So this is where the attention regularization comes in. Right. So start with prior knowledge P, then slowly evolve the attention map as you go. So that is basically the motivation for graph convolution transformer.
Sorry to interrupt.
Sure.
One more question. How do you compute the conditional probabilities? Is it just count the frequencies of co-occurrence?
Exactly. We I just counted frequency. So you can count the independent occurrence probability by just simply counting how many codes occur in which number of visits, and then once you have that, you can also count the joint probability of how many times this pair of codes occur at the same time in some visits, and then you can do conditional probability.
All right, I see. Thanks.
Right. Cool. All right. So given that, so we try to see if this architecture actually learns meaningful structure, because we don't know if it'll learn meaningful structure. So unfortunately, at the time, I couldn't use the EHR dataset where the reason information was already there. So I had to synthesize simulated EHR where the graph structure was already there, so because I simulated it, and then try to see if this GCT graph convolutional transformer model learns the true structure well. So there I use two sets. So synthetic ones are the ones that I created where the true graph structure is known, and EICU is just one of the open source EHR dataset where true graph structure is unknown. So the synthetic dataset is used for proof of concept or validation, and EICU is actually used for real world applications. So what I did with the simulated dataset is basically graph reconstruction. So what I try to do here is given a pair of codes in a visit, try to predict whether there should be a connection between the two or not. So simply this is graph reconstruction task, and GCNP is a graph convolutional neural network where you use adjacency matrix with this P matrix only. So this is simply a prior knowledge driven graph neural network, and GCN random is just using random graph, and then shallow and deep are just adding the codes as a set representation, just adding the code representation, adding the word code representation vectors, just simply summing them up to represent the visit. And then transformer is purely data-driven self-attention process, and GCT is actually the hybrid between GCNP and transformer. And you can see that GCT actually outperforms all the other the baselines as far as graph reconstruction goes. And you can see actually GCNP does pretty well. So this conditional matrix P is actually a good indication or good proxy of representing the ground truth structure, even though it's purely conditional probability driven. It is still a pretty good proxy. So that's a good lesson. And given this, so we validated that the GCT can learn pretty good meaningful structure. So we tested them out on the real world data set EICU, and we did 2 prediction tests, which is readmission prediction and mortality prediction. And for readmission prediction, GCT did outperform all the other models by some margin, but for mortality prediction, not so much. So you can see that the prediction performance for GCT and deep and transformer, they're all like more or less the same. But for readmission, there's a non-trivial gap. So you can assume that different prediction tasks require different levels of graphical knowledge. So maybe mortality prediction, you can just simply sum all the relevant information up and then just make prediction, and that's okay. But for readmission prediction, maybe you need to learn the hidden relationship between the codes. And this is actually one of the qualitative examples that I used to visualize that the GCT does learn meaningful structure. So we are using the synthetic data set where there's a visit node here, and this is all the codes that occurred in this visit. And what we're doing is trying to learn the structure, the ground truth connections, using transformer and GCT, and we're comparing the results. Here, the red mask here. So we are looking at the connections in terms of this node. So this node is connected to visit, obviously. This is diagnosis code. And these red bars indicate the true connections. So these 4 treatment codes. So that is the true connections that the model needs to learn. And if you look at transformer self-attention block 1 to 3, we're losing three layers transformers. So self-attention block 1 to 3, kind of naturally, the transformers start with a uniform attention distribution, because in the first layer, transformer doesn't know which codes are available. So it needs to just look at all the codes at the same time. And in the second layer, transformer starts to attend to relevant codes, so important codes. So it does kind of try to focus attention on these 2 nodes, which are actually part of the true connections, but it does not attend to all the other nodes, unfortunately. And in the third block, in the third attention map, it starts to diverge. So it starts to attend to other codes, which are not actually the connected codes. So the self-transformer is just going everywhere, basically. But if you use GCT, it starts with the prior conditional probability matrix P, which looks like here. So I didn't fully specify. So the red bar is the true connection, and the blue bar is the attention or the learned connection. So in the first layer of GCT, this is conditional probability based adjacency matrix. So you start here and then you evolve procedurally. In the second block, this is the learned attention. So it starts to try to distribute its attention to other codes. And then the third block now is converging to the true connections. Pretty much, it's doing a pretty good job refiguring out, rediscovering the true connections, which are the red strips here. So you can see the clear difference between purely data-driven approach and a hybrid data-driven plus prior knowledge-driven approach. So you can see that this is why GCT learns the structure better than transformer, and it leads to better prediction performance for at least for specific tasks. So the conclusion is that even if you don't know the ground truth structure or the reason codes, or if you suspect there is a lot of noise, you can still do better than simply just adding adding the codes up, code representation vectors up to represent the visit, you can still do better than backup features, basically. So, which is based on using graph attention and combination of graph attention conditional probability. But this is just a start because I only assumed that this only works for outpatient records. But if you think about like admitted patients or ICU patients, their graph would change over time because they stay in the hospital for a couple of days. So like even for a single visit, codes will have timestamps. So like this first day, second day, third day, different, maybe the same codes or same medications are given over and over again. So the graph will be dynamically changing over time. So maybe what is the best, we could try to think about what is the best way to represent dynamically or temporally evolving graph, and how to handle even more feature types, like different modalities like images or clinical notes or spectrograms or demographic information that I introduced in the very beginning. So this is just the beginning. And I think I used my given time, actually. I do have a couple of slides that are more focused on multimodal learning. So if you guys can give me maybe one or 2 minutes, I can just briefly go over the slides.
Yeah,
if that's
absolutely.
okay.
You can take your time. Like we anyway upload the talk, so people who had to drop off can drop off, and people who still have time can stay. So feel free to go ahead.
Okay, sounds good. Thank you. All right. So the third or the final note is multimodal learning with transformer, which is the more recent research interest that I'm having. So there are a lot of BERT-based vision and text multimodal learning these days, and these are just few of the examples that just came up off the top of my head, like video BERT, VIL BERT, InterBERT, Unified VLP, Uniter, Pixel. There's basically a lot of BERT variants that claims that they are doing vision text multimodal learning, and they actually do work pretty well, at least based on their paper. And I'd like to focus our attention on one specific example, which is PixelBERT, because all the others are a bit more it's either video based. So VideoBERT is actually using video and video captions to learn representation. So it's not really usable in our case, which is a chest X-ray and radiology report multimodal learning. And these four do use images, but they also use off-the-shelf object detectors like faster RCNN. So in order to capture what kind of objects lie in an image, they use off-the-shelf object detectors, so which is not usually available in medical domain. So this is out of the picture. So what we focus on is a PixelBERT, which is using images only without any object detectors or any like additional modules. So simply I'd like to just introduce one example from PixelBERT paper, which is that even without the object detectors, the model, with given enough number of samples and given enough of training time, the model starts to understand the connection between words or text and pixels. So for example, this is all transformer based, so you can actually try to see what is the attention of the word, like which word is attending to which pixel region. So for example, here this is the true image, and this is true sentence. A dog sits on the grass with his frisbee. And if you look at what the model is doing, when the model is when embedding the word dog, the dog is attending to the dog pixel here, which is highlighted here. And not maybe this is a bit like, not doing a good job, but at least this part is doing a good job. And then the word grass is attending to all the grass, and the word frisbee is actually attending to here. If you look at the frisbee here, it is attending to frisbee. So even without the object detection module, if you have enough amount of data, then the model will start to learn meaningful relationship between totally different two modalities. So inspired by this approach, we actually thought we could do the same with chest X-ray and radiology report. So there's a data set named Mimic CXR, which consists of a lot of images and a lot of radiology report pairs. And typically it looks like this. So a single study consists of multiple, like one or more chest X-rays, like frontal view, back view, side view, that kind of stuff. And then each study comes with a single report, which consists of different subsections like history, comparison, impressions, findings, techniques, different subsections. So if the model can learn a meaningful connection between the image domain and the text domain, and if you can put both information at the same time to the model, then the maybe model can do interesting stuff like obviously diagnostic classification, or retrieval, like like search engine. Given a report, you can try to retrieve out of your database the most relevant image, or vice versa. If given an image, you can try to retrieve the most relevant report. So that's also possible. And visual question answering is also possible. If you, for example, like the doctor could ask what kind of problem is there in this picture, then the machine can generate, such as there's like a nodule in the lung, or the lung looks opaque, something like that. And you can also do generation, such as given an image, just like image captioning. This is like radiology report generation. Given an image, you can ask the model to generate the report by itself without human intervention. So a lot of interesting stuff can be applied as a downstream task, given a model that understands both modalities at the same time. So I won't go into detail about so this is an ongoing work. This is actually going under review, so I won't go into detail. And I mean, the detail is not that different from all the previous BERT-based models like Pixel, but United BERT. It's not that different. You have a gigantic BERT model, and then half of the side you put the pixel fibers, and half of the side you put the tokens, and that's it. And then you do a self-attention with BERT-based masked language modeling. But the result is quite interesting. So what we're showing here is a text to image retrieval. So given a radiology report, we want to retrieve the relevant images and rank them by their relevance. So this is the query here, and this is query, which is a radiology report. And I think this is just the impressions findings section, and the colors represent different diagnoses or different findings, basically. So the orange one is orange sentence is representative or indicative of label support devices. So the label is actually coming from the data set itself. So support devices, and the green sentence is relevant to enlarged cardiomediastinum. I'm not sure what this is. And the blue sentence represents lung opacity. And the model retrieved a lot of images. But if you just look at top 3 and a bit like a low rank example, you can see. Actually, no, I'm not a radiologist, so I'm not sure if these 3 images are actually right images to retrieve. But luckily, the rank 1 image is the actual original paired image to this report. So that is good news. But I'm not sure if rank 2 or rank 3 it does correspond to this radiology report. But at least when there must be the same paired report for all these images. So you can run the NLP tool to extract this kind of label, and when you do, they do extract the same set of labels. So at least that's the good news. But I haven't actually asked the doctor to take a look at these examples and see if they are actually the same as this report. But at least by the NLP tool, it says it does. And here this is like a rather low rank image, and when you run the NLP tool, it says cardiomegaly, and I guess the heart does look a bit large, and it has nothing to do with this report. So I guess this is a bit hard to explain as a non-expert, but at least this one is a bit easier to understand, which is image to text. So image is being used as a query, which looks like this, and then the relevant label was lung opacity and cardiomegaly. And when you retrieve the relevant reports, all of them, and then rank them by the relevance, then luckily again, rank 1 is the original paired report. But if you look at rank 2 and rank 3, they do contain similar information, like heart size enlarged because of cardiomegaly, and lung opacity here, there are some opacities. And again, here, cardiomegaly, and then some statement about how lung opacity is there in the image. And if you look at low rank examples, it just says no finding. So pretty irrelevant. So at least this much we can understand that it's doing a good job. So this is the retrieval example, and this is the generation example. So we're asking the model to write the report by itself. So this is the true image, and this is the actual report written by the physician, and this is the one that was written by our model. And the original report says ET tube, whatever, and then NG tube is such and such and such, blah, blah, blah. And the generated report all says endotracheal tube something and nasogastric tube something. So this is actually the unabbreviated form of ET tube, and nasogastric tube is the unabbreviated form of NG tube. So it's interestingly, I'm not even sure if there are any tubes here because I'm not a physician, but at least the model understands there are tubes here, which can be written as endotracheal tube instead of ET tube, and which can be written as nasogastric tube instead of NG tube. So the model already has better domain knowledge than I do by looking at hundreds of thousands of examples. So, which is pretty interesting. And this one is another example. So this is the actual example, image, and this is the ground truth original report, and this is generated report. And the students, they found out that by doing some Google search about medical journals and that kind of medical text, they found that the VATS procedure has a very tight, very close connection with what is written here with the extubation and the nasogastric tube. Because if you go under a VATS procedure, you have these nasogastric tubes. So after the VATS procedure, you have to extubate them. So if you have this, if the model says this, then it kind of understand that was a VATS procedure. So it's also doing a pretty good job. And the last one is the attention behavior. So just like what we've seen with the dog and the frisbee example, you can do the same with the chest X-ray in the report. So this is the actual X-ray, and this is the one of the sentences written by the physician. And if you look at the attention given from the pulmonary edema, this red circle is where these two words are attending to. And I've asked a couple of doctors if this is correct, and they say that the model is actually attending to the right region, because this white thing here they shouldn't be here, because the lungs should be like black and clean. But if there is certain noise here, then it could be indicative of edema. So it is looking at the right region. And the pleural effusion is these two words are looking at this region. And I looked up what pleural effusion is, and it says that like your lung, your lung is collecting water somewhere. So there's like water somewhere, and it should be in. Usually, when there's water, it should be in the below at the bottom of your lung. So when I asked a couple of physicians, they asked that like this region does look like water. So the model is doing a good job looking like pleural effusion, connecting pleural effusion to this region. So it's kind of understanding what it does. And another example, this is the image, and for this heart-sized borderline large, this statement is attending to these regions, and especially strong attention is given to the heart section, or at least the boundary of the heart section. So I think it's doing a good job. And also a couple doctors confirmed that this, I guess, doing a good job. But we are far from doing a rigorous user study. So this is just a couple of qualitative examples. But at least I have no idea what pulmonary edema is, but the model seems to know better than I do. So I guess that's very encouraging. Right. I guess I can just skip through these. Another form of multimodal learning. So this multimodal learning. So previous one is image and text multimodal learning. This is graph and text. So far I've talked about how how EHR dataset can be seen as a graph. So we have a structured information, and we also have a unstructured discharge summary. So here, this part is structured knowledge with maybe some information loss, because all the fine-grained granular information will be lost when you convert text into like a database tabular form. And this part is unstructured, but they do contain a lot of fine-grained images, fine-grained information. So hopefully, maybe it is a good idea to use both information at the same time maybe they're at the complementary relation. They have a complementary relationship. So if you can learn both modalities at the same time, then maybe we can do a lot of interesting tasks, such as generation or classification, or finding errors in text, or finding errors in your EHR. Like if you enter wrong value in the EHR system, but the right value is written in the discharge summary, maybe we can find out that there's an error in your EHR. So something like that. So we can find out errors or typos, graph link prediction, graph node prediction. We can do a lot of kinds of stuff. So this is also another. So we have this. We've done this with the graph. We've done this with the BERT-based architecture again, but where the one part is a bit like graph encoder and another part is a bit like text encoder, and then we do multimodal learning. And then when you do graph retrieval and text retrieval, we get the same good performance. Just like the image to text and text to image retrieval, we can do graph to text or text to graph retrieval. So when given query, or when given a discharge summary as the query, trying to find the most relevant graphs, this is rank 1, 2, and the last. And you can see that unfortunately here, rank 2 was the original pair, and rank 1 was not the original pair. But at least these two graphs contain very similar set of codes, similar set of nodes. So like these three are the same. I think these three are the same diagnosis codes here and here, both rank 1 and rank 2. And this blue box is the same procedure code, rank 1 and rank 2. And there are some different set of codes here, but at least these four are the same. So you can see that the model understands the relationship between text and graph a bit better than expected. This is text generation. I'll just go skip this one. This is just basically given a graph trying to write the discharge summary, but you can see that I'm gonna share the slide again, so you can take a look at them if you're interested. We're just doing different conditional generation. And lastly, this is the graph attention behavior analysis. So here, this is the text part, and this is the node or graph part. And you can see that even though I haven't actually told the model that this text is the same as this node. I didn't do that obvious. I just gave a bunch of like tens of thousands of examples and hopefully they figured it out, and they did figure out. So for example, the word kidney is strongly attending to the node acute kidney failure, and the word HIV is strongly attending to these two nodes, which is asymptomatic HIV and hepatitis C, interestingly. And it was my students reported that a lot of HIV patients do end up with hepatitis. So maybe that's why HIV is attending to both hepatitis and HIV at the same time. So, but we haven't actually rigorously done a qualitative study yet. So this is just a couple examples that we found to be interesting. Right, so yeah, this is the end of the talk. So thank you very much for staying around. I've used too much of your time. This is already 1 hour and 20 minutes. So thank you for staying around. And if there are any questions, I'll be glad to answer them.
Yeah, thanks so much, Edward. I think you gave a very comprehensive summary of all of your work. And I think I personally learned a lot, and I'm sure all of the others did as well. So before we move on to the questions, let's thank our speaker with some virtual applause and open up the floor for questions. I'm sure there are probably others who had a lot of questions, but we'll either ask them to email you directly with the questions, or we also have a mechanism on our website where they can post questions and we can forward them to you. So for the people here, if you have any questions, feel free to ask right now. And
I have a question about the the graph convolutional transformer. Work. So I think you show some results. Oh yeah, these two slides. These are on the synthetic data. So have you done this similar analysis on the real data? But I know you don't have the true connections. You don't have the ground truth in a real data set. But have you like qualitatively look at some examples and see whether they make sense or not?
Actually, that's a very good question. Unfortunately for EIC, this data, no, but so when I was working at Google, there were a lot of EHR data sets, and one of them did have actually the ground truth connection information. So, and it was really gigantic data. I think it consists of maybe like at least 5 million patient records or something. So when I actually ran this algorithm on that, not even GCT, just if you just run transformer, for example, just selfattention on those millions of patient records, then it actually learns pretty well the ground truth connection, even without the conditional probability matrix and all the fancy stuff that's going on here. Even without this, just if you just run selfattention algorithm on millions of patient records, then it actually learns the true connections pretty well, pretty accurately. So the lesson is, if you have infinite amount of data, you don't need fancy algorithm. You can just run transformer and that's it, which is already proven by GPT-3 and BERT, and if you have access to all the data in the world and just run 50 stacks of transformer, then magical things happen. So I'm guessing the same would be also applied. Same principle can be applied to EHR. If you have all the patient records in the world and you just stack up 100 layers of transformer, then magical thing will happen. And unfortunately, I don't have the kind of resources.
Okay.
I actually have a couple of more qualitative questions. So, so in your case, you made the design choice to treat all the diagnosis as one level and all the treatments as another, and then prevent connections between like things of the same layer, for instance.
Right.
So have you thought about the case where like first a patient comes with a certain diagnosis, the physician makes a diagnosis, but based on the treatment results, the diagnosis change. So the nth diagnosis might actually be a reflection of the n-1th diagnosis in the same visit, but they're not actually in the same level. So I wonder how the graph should change. Like, should there be an ordering? Should it be a sequence? Action, result, action, result.
Yeah, that's a very good question. So there is obviously a latent connection between different layers in each visit. So there is a sequence of visits, first of all. We can maybe look at. Maybe this is enough. Yeah. So there's a sequence of visits, and each visit consists of diagnosis layer and the treatment layer. And what you're suggesting is, instead of just visits being connected, maybe there should be connections between the diagnosis layer and the treatment layer between visits. And that is a valid suggestion. And I think, I'm not really sure on this, so maybe you'll have to look up, but one of my co-authors, Zen Zhu, he has a paper called Mufasa. I'm not sure if the name is correct, but his, so before I left Google, he was working on your idea actually. So he thought there should be like a layer-wise connection or layer-wise sequential connection between. There should be like a visit layer connection. There should be diagnosis layer connection. There should be treatment layer connection. Something like very similar to your idea. So he was trying to come up with a better model than this. So, and he has a paper that named Mufasa. I'm not exactly sure if that paper was the follow-up of his idea or if it's a whole new idea, but maybe it's worth taking a look. Yeah, definitely. But your idea is very, very valid. Yeah.
Got it. Okay, I'll take a look at that paper. And one other question, if anybody else has a question, I can wait, but if not, so what's the difference between symptom and a diagnosis in your framework? Like, for instance, like a cough and a fever and fatigue might be symptoms, but the actual diagnosis might be, okay, this person suffers from pneumonia, say. So would those all be treated as diagnosis in some case, or like is one a subset or a superset of another?
No, actually, yeah. In my case, there's no difference between symptoms and diagnosis because they're all just ICD-9 codes in this data set. Or actually, in EICU, there's no ICD-9 code, but still, it's just different subset of diagnosis codes. So, and these are all actually codes. So that is the main limitation or one of the things that I'm not really happy about the work so far, because I'm only using codes and I'm not actually using, for example, like lab values or side information such as like start date of your medication, end date of your medication, or dosage of your medication. And these days I'm trying to use them as cleverly as possible, but I can't seem to find the way. Because, so for example, if your medication is so your medication name is Tylenol and your medication dosage is like 2 tablets and your medication route is like oral, something like that. Like there should be like different columns for your single medication order. And if you try to incorporate, if you try to inject all those information into your model, and sooner or later your model will look like really it would have a hard time differentiating different sources of information. And I was thinking about converting them all to just text, just like medication name is Tylenol and its dosage is 2 tablets, something in a more natural text form. But then the problem is, like these recent like BERT variants or these like gigantic language models, they're not really good at understanding numerical values. Like it doesn't understand that 10 is larger than 5 or 0.1 milligram is, or for example, like 5 milligram is larger than, 5 gram is larger than 100 milligrams. It doesn't understand the relationship between different numbers. And if we are to actually maximize the usage or or impact of using those numerical values or different sources of information, there should be like a more powerful model that can actually understand what it means instead of just pouring just data into the model in a rather naive way. So yeah, that is one of the research projects that I'm actually trying to focus on these days.
That's very cool. And,
Thanks.
And then I guess one final question to maybe wrap this up. EHRs are like all the work that you've described is very unique to the US because they structure their information in a certain way. So on a global scale, do you think there is scope to integrate like multiple countries, or like from your experience, like have you also worked with data sets from, let's say, South Korea, which are what are the similarities and differences between EHR modeling in that perspective?
I didn't hear the last part. All the similarities and differences
between modeling EHRs from different countries, and so can a model that is trained on, say, US EHR be applicable to models from data from other countries and so on?
I guess I can answer that question in two perspectives. So one is the distribution of the demographic is definitely differently. Like there are certain diseases that are, where Caucasians are more susceptible compared to Asians, and there could be a vice versa. So if you have a model trained on, specifically for this some cohort, and then try to use that in another cohort, completely different population, then it probably wouldn't work. So in that aspect, there's definitely, I guess, like machine learning models, machine learning topics such as like domain adaptation or out of distribution detection, that kind of thing is relevant. But more interesting, not more, but to my interest, what I'm more interested in is the different schemas or different data formats between different countries, and not just different countries, but different hospitals. For example, like hospital A in Korea has a different database schema, which is, so like, all hospitals have different database schemas because they're all focusing, they're using different EHR solutions, or maybe they're focusing on different demographics for some reason. And if you want to use the same code or same model trained on the use for this hospital on another hospital, it'll never work because data formats are different. So a lot of people use CDM like OMAP or FHIR as a middle ground. So a lot of hospitals in Korea, like especially like large top 20, maybe top 30 large hospitals in Korea, they're all working on trying to convert their internal data into OMAP format so that at least like the formats are unified. But the problem is the people who are converting internal data to OMAP at each hospital are different people. So they have different bias. So the end product will be, the quality of the end product is not guaranteed. So even OMAP or CDM is not the best solution out there. So that is also one of the things that I'm actually trying to focus on. So for example, like if you do federated learning with a lot of different hospitals, then different formats would be definitely a problematic. And then if you only rely on OMAP based approach, then the quality not being guaranteed, it'll lead to suboptimal performance. So for example, if you can somehow come up with a way to use only text, for example, we're only going to use discharge summary, then all hospitals have discharge summaries at least. So if you're only using discharge summaries, then at least if they're all written in the same language, either it could be Korean, it could be English. If they're all written in the same language, then at least there's no format difference between the language. So in that case, we can do pretty much robust, federated learning based prediction or whatever, or finding similar patients or whatever. But if you want to do better than that, then we're going to have to come up with a way to how to unify different formats, or at least how to overcome with better machine learning techniques. So I think that is a bit more interesting, engineering wise. That is more interesting compared to different distribution for different countries.
Awesome, thank you so much.
All right, thanks.
It looks like we don't have other questions, so thanks again for spending a lot of your time and especially getting up so early for this talk.
Right.
And we'll be uploading the recording on YouTube, and we'll also send you a link so you can publicize it as you see fit.
Okay, thank you very much.
Thanks again.
Yeah, thanks, Ego, again.
All right, thanks for invitation again, and thank you guys for staying around. I'll see you guys soon.
Yeah,
Bye-bye.
Thank you.
Bye.
Bye-bye.
Mhm.
Bye.